Today we shall study about invertible matrices. In the last session I told you every matrix is not inversible. For a rectangular matrix we cannot speak of inverse, and every square matrix is not inversible. If capital A is a square matrix of order n, and if there exists a square matrix capital B of the same order, such that A into B is equal to identity matrix is equal to B into A, then we can say that B is the inverse of A, and we write B is equal to A inverse, A power negative 1 means A inverse. In such a case, we say that A is invertible, or inverse. I told you even every square matrix is not invertible. We can consider one case where inverse exists and one case where inverse doesn't exist. So first of all, let us consider this square matrix 2 by 2, 2, 3, 5, 7. This is a 2 by 2 square matrix. Here we can find a square matrix negative 7, 3, 5, negative 2, and we can see that when we multiply these two matrices, we can have 2 into negative 7 plus 3 into 5, that is 1, then 2 into 3 plus 3 into negative 2, that is 0, then 5 into negative 7 plus 7 into 5, that is 0, then 5 into 3 plus 7 into negative 2, that is 1. So what we are getting is identity matrix, So we can say that this matrix, second matrix, is the inverse of the first matrix and vice versa. So here we have the inverse of this matrix, but if we consider another square matrix, say 2, 3, 4, 6, 2, 3, 4, 6, this is a 2 by 2 square matrix, but we cannot find a square matrix so that this matrix, say capital A, multiplied by this matrix, say B, is equal to identity matrix. Here we cannot find such a matrix B, therefore this given matrix capital A, 2, 3, 4, 6, is not inversible. Because we cannot find a B matrix here such that AB is equal to I is equal to B. Now we can see that for this matrix 2, 3, 5, 7, we had the inverse, that is negative 7, 3, 5, negative 2. Now we cannot find another inverse for this. That is, if the inverse exists for a matrix that is unique, it is no guarantee that inverse exists, but if it exists, it is unique. How to prove it? For example, we are going to prove the uniqueness of inverse. A square matrix, if its inverse exists, has a unique inverse. Let capital A be a square matrix. Capital AB, a square matrix. If possible, and whenever we say in mathematics if possible, we know that it is not possible. And if possible, let capital B and C are its inverses. If possible, let capital B and C be its inverses. Then what will happen? Since B is the inverse of capital A, we can have A into B is equal to I is equal to B into A. Also, since C is the inverse, what we can write? A into C is equal to I is equal to C into A. Now what we shall prove is, that B is equal to C. Consider B is equal to, we know that B is equal to BI, because we can multiply any matrix by identity matrix without altering it. And what is I now? I is nothing but AC. You know, AC is I. So we can write in place of I AC. And now here we can apply associative law. Associative law says B into A into C. That is same as B into AC. So BA into C. What is BA? BA is I. So we can write BA is I. So we can write IC. And identity matrix into C is C. So we could prove that B is equal to C. That's all. Again you can see that inverse of a product, what it will be. For example, AB is the product and its inverse AB inverse. That is equal to B inverse A inverse. How to prove it? You know that if capital P has inverse P inverse, then what is P into P inverse? P into P inverse will be identity matrix. Therefore, for the matrix AB, if you multiply it by its inverse, that is AB inverse, that is AB into AB inverse, that is equal to identity matrix, because P into P inverse is I. So therefore we can write AB into AB whole inverse is identity matrix. Now we can pre-multiply. Pre-multiply means we will multiply from the left hand side of the equation. That is, we shall pre-multiply this equation by A inverse. That is A inverse AB into AB whole inverse. That is equal to A inverse into I. That is A inverse. It is A inverse. Now using the associative law here, we can write A inverse A into B. That is by associative law into AB whole inverse. That is equal to A inverse. Now you can see A inverse A. What is A inverse A? That is identity matrix into B into AB whole inverse. That is equal to A inverse. Now what is IB? IB is B only. So we have B into AB whole inverse is A inverse. Again by pre-multiplying this equation by B inverse, what will happen? B inverse B AB whole inverse is equal to B inverse A inverse. Again by applying associative law here, that is B inverse B into AB whole inverse is equal to B inverse A inverse. Now what will happen? So that is equal to, what is B inverse B? that is identity matrix. Now identity matrix into AB whole inverse is B inverse A inverse, which implies AB whole inverse is equal to B inverse A inverse. Hence the proof. Now, how to find the inverse? For example, let us consider the matrix. Say capital A is equal to 2, -1, 1, 2. We can find its inverse in many ways, but here we shall find the inverse of this matrix by elementary transformations. We studied already there are 6 elementary transformations for operations, 3 of which are due to rows and 3 of which are due to columns. So here we shall apply elementary row transformation and elementary column transformations to find the inverse of the matrix. So here we shall find the inverse of this matrix by elementary row transformations. For that we shall write A is equal to IA. We know that IA is nothing but A. The inverse of capital A is equal to 2, -1, 1, 2 using elementary row transformation. Elementary row transformations. Elementary row transformations. So, what we have to do? We have to write A is equal to IA. What do you mean by? What is A? A means 2, -1, 1, 2. That is equal to identity matrix 1, 0, 0, 1. That is I2. And A as it is. We are not going to expand this A because we are not going to change it till the last term. Now, our demand requirement is that here we should have 1 because we have to make this matrix as the identity matrix. So here it is 2. Now you can see that just below there is 1. So in order to get 1 in place of these 2, we can just interchange the 2 rows. That is, our operation will be R1 interchanged with R2. Then what will happen? 1, 2, 2, -1. And the same operation you have to do on the right hand side also. That is 0, 1, 1, 0 into A. Now our next target is to bring 0 here. So you see there is 1 above. So if you take 2 times of first row and subtract it from the second row, automatically we can have 0 there. So our operation will be R2 transformed as R2 minus 2 times R1. 2 times R1. Now what will happen? Let us see. That is, there is no change in the first row. So we can write as it is. There is no change. And the second row change is R2 minus 2 times R1. So 2 minus 1, 2 times 1. That is 0. Then -1 minus 2 times 2. So what will happen? That is -1 minus 2 into 2. So -5 it will be. The same operation we have to do here also. That is first row, no change. And the second row, 1 minus 2 times 0. That is 1. Then 0 minus 2 times 1. So -2 and no change with A. Now our next target will be to bring 1 at this place. So what we can do is, we can transform the second row as -1/5 into R2. So what will happen? Let us see. That is, there is no change again in the first row. We can write it. then 0 has no change, and negative 5 becomes negative 5 into negative 1 by 5. So that will be 1. Then we do the same operation on the right hand side also. That is 0, 1, no change. And we have to multiply the second row by negative 1 by 5. So negative 1 by 5, then 2 by 5. Is it? Then into A. Again our target will be to bring 0 to this place, so that the left hand side matrix will be I2, identity matrix of order 2 by 2. So that we can do very simply. What we have to do is, here you can see that here it is 1. So we will take 2 times. So R1 transformed as R1 minus 2 times R2 this time. So what will happen? Changes with R1. So be careful. So 1 minus 2 times 0, that is 1 only. 2 minus 2 times 1, that is 0, then 0, 1. So left hand side our target is achieved, that is I2, identity matrix. And right hand side, then 2 times negative 1 by 5 subtracted from 0. So what will happen? That is 2 by 5. Then 1 minus 2 times 2 by 5, that is 1 minus 4 by 5, that is 1 by 5. And denominator, second row, no change, that is 2 by 5, 2 by 5 into A. So what we could obtain is identity matrix is equal to sum B. So you can see this is your matrix B, then B into A. So you can see that is BA is equal to I. Therefore inverse B is A inverse. This is nothing but this matrix, that is 2 by 5, 1 by 5, minus 1 by 5, then 2 by 5. That's all. This way we can find the inverse of a matrix by elementary row transformation. Now we can find the inverse of this matrix by using elementary column transformations. Elementary column transformations. Find the inverse. Find the inverse of the matrix. Same matrix we can consider 2, negative 1, 1, 2. Now here you understand we cannot apply any row transformation here. One more thing I must tell you. Once we started with the elementary row transformation, we cannot switch into elementary column transformations and vice versa. You have to stick to the same operation. That is, if it is elementary row transformation, always elementary row transformation till we reach the identity matrix is equal to BA step. And if we start with the elementary column operations, then we cannot switch back to elementary row transformation. We have to stick to elementary column transformation. Okay, so here again I told you one more step. That is, if you are going to apply elementary column transformation, what's the starting equation? Starting equation will be A is equal to AI. A is equal to AI. That's a very important step. Now what is it? That is 2, negative 1. 1, 2 is equal to. First A, there is no change. We will keep positives. And I means 1, 0, 0, 1. Now here we have to bring 1 at this place. So very simple, here we have negative 1. So we shall operate C1 transformed as C1 plus C2. So what will happen? Here 2 plus negative 1 is 1. Then 1 plus 2 is 3. Negative 1, 2, no change. That is equal to A into. Then we have to add second column to the first column. That is 1 plus 0. That is 1. 0 plus 1. That is 1. Then 0, 1. There is no change. Now our target will be to bring 0 here. So in order to bring 0 here, what do we have to do? So we can add, here we have 1. So why don't you add C2 transformed as C2 plus C1. C2 plus C1. Then what will happen? Let us see. 1, 3, no change. Then 1 plus -1, that is 0. Then 5. Then that is A into, then 1, 1, no change. Second, 1 plus 0, that is 1, then 2, like this. Again, what we have to do? We have to bring this place 1. So, for that, C2 transformed as 1 by 5 C2. So, what will happen? Let us see. 1, 3, no change. Then 0, no change. 5 into 1 by 5, that will be 1. That is equal to A into, then 1, 1, no change. Then 1 by 5, that is 1 by 5. Then 2 by 5, like this. Now, again, our target will be to bring 0 to this place. So, what we have to do is, so you can see here it is 1. So, if we transform C1 as C1 minus 3 times C2, this 3 will be 0. So, let us operate it. That is, changes in the first column. So, be careful. So, you can see that is 1 minus 3 times 0, that is 1 only. It will not be altered. And 3 minus 3 times 1, that is 0, then 0, 1. So target is identity matrix. And then here you can operate the same thing. So what we have to do? That is 1 minus 3 into 1 by 5. 1 minus 3 into 2 by 5. And second column no change. So 1 by 5, 2 by 5, and in. So that is equal to A into, now we can operate, that is 1 minus 3 by 5. So that is 2 by 5, then 1 by 5, and you can see that is negative 1 by 5. Negative 1 by 5, then 2 by 5. And what the equation we reach? Identity matrix is equal to A into B, where B is this, and this will be the inverse of A, that is A inverse. And you can verify the same answer we obtained previously also, that is, you can see, what was our answer? That is 2 by 5, 1 by 5, 81 by 5, 2 by 5, 2 by 5, 1 by 5, 81 by 5, 2 by 5. So, here also we got the same answer, that is 2 by 5, 1 by 5, 81 by 5, 2 by 5. So this way we can proceed with it. And I will give you one homework for you. Find the inverse, find the inverse of the following matrices by elementary transformations. By elementary transformation. This is your homework, please. So, first matrix will be, that is 1, 2, 3, 4. This is very easy. You have to find its inverse by two methods, by elementary row transformation and by elementary column transformation. Please do it. Again, one more case we have to deal with. Now let us find, if possible, the inverse of the matrix 10, negative 2, negative 5, 1. So here we can apply elementary row transformation or elementary column transformation. So let me apply elementary row transformation. For that, what's the equation? We have to start with A is equal to IA. We have to start with A is equal to IA. So what is A? A is 10, negative 2, negative 5, 1. And what is identity matrix? 1, 0, 0, 1 into A. Now, our target is to bring 1 here. So what we have to do is R1 transformed as 1 by 10 R1. Then what will happen? Here we shall have 1, then negative 2 into 1 by 10. That is negative 1 by 5. Then there is no change with the second row. So we can write as it is negative 1, 5, and that is equal to. Here also the change, that is 1 by 10, then 0, then 0, 1, and into A, like this. Again, we have to bring 0 at this place. So here, negative 5 is here, and 1 is above. So we can apply R2 plus 5 times R1. So what will happen? So that is, you can see 1, negative 1 by 5. There is no change. And here, we have to bring 0. So if we add 5 times first one, that is 0 we can have. And here what will happen? That is 1 plus 5 times negative 1 by 5. That also 0 is equal to 1 by 10, 0, 0, 1 into A. And this is very interesting. We obtained all the elements in a particular row or column. In a matrix, either left hand side or right hand side, then we must understand that its inverse does not exist. Once again, since we obtained all the elements 0 in the second row, all the elements of the second row are zeros here. Let's see, 0, 0. We cannot proceed further, and here we can write A inverse doesn't exist. A inverse doesn't exist. And one more homework I can give you. Find A inverse. Find A inverse. If possible, find A inverse. If possible. For the matrix. For the matrix. Capital A is equal to 2, 3, 6, 4. 2, 3, 6, 4. That is first one. And second, capital B is equal to 2, 3, 4, 6. And one more question. That is, capital C is equal to 1, 3, negative 2, negative 3, 0, negative 5, 2, 5, 0. So, please try all this one. I will give you a clue. For this matrix, we can have the inverse. And for this matrix, we cannot have. And here, you can find the inverse. Please do it. Please do it. Please do it. Now, one more thing. Is there any other way to find the inverse of a matrix? Yes, of course, we can find inverse of a matrix in many ways. Another method is that if capital A is equal to, say, 3, 1, negative 1, 2, first of all, verify that. First of all, verify that A square minus 5A plus 7I is equal to O. O means 0 matrix. This you know already. How to verify this equation that we explained in the last section. So, I will give you the clue once again. You have to find A square first of all. Then you will find 5 times A, that is multiply A by the scalar, non-zero scalar 5. Then 7 into I. What is I? I means here I2, that is 1, 0, 0, 1. That again is scalar multiplication. So you can do it. And after verifying this equation, how to proceed? Now we have A square minus 5A plus 7I is equal to O. Now if we post multiply, that is A square into A inverse minus 5A into A inverse plus 7I into A inverse is equal to 0 matrix into A inverse, that is 0 matrix. We know that if you multiply any matrix by 0 matrix, and answer will be 0 matrix, therefore that is 0 matrix. Now, what is this equation? Now, just like in the index laws that you learned in ordinary algebra, here also you can apply. Some theorems are there, but it is beyond the scope of plus 2 level. So, just you recollect, just like the exponential laws that you learned in algebra in your previous classes, you can apply here, that is A only, minus A inverse. You know what is A inverse? That is identity matrix. That is 5 into identity matrix. Plus 7I A inverse. 7I A inverse. So what it is? That is 7 into A inverse only. That is equal to O. 0 matrix. Now you can see that is 7A inverse. You keep this side and you take 5I minus A to that side. And this equation yields us A inverse is equal to 1 by 7 5I minus A. So you can see A inverse is given by this equation. And how to simplify this equation? That is very simple. We will write 1 by 7 here, 5 here, and identity matrix, that is 1 0 0 1 minus A is given to you. A is given to you. What is your A? A is nothing but 3 1 negative 1 2. A is nothing but 3 1 negative 1 2. So you can write it 3 1 negative 1 2. So you substitute that one and you simplify. Then that will be your answer. That is A inverse. A homework for you. For the matrix, capital A is equal to 1 2 3 4. Verify that A square minus 5A minus 2I is equal to 0 matrix, and find A inverse, So a very simple question I told you. First of all, you have to verify this equation, and by post multiplying this equation by A inverse, you can proceed with ASAP. That's all for today. We shall come with another topic in the next class. Thank you.